We recently uploaded our 45-minute-long documentary on Hermeus. It was the best performing video we've uploaded in quite some time, so I figured I would share more of what we learned at Hermeus with you. What you are about to watch is a mostly uncut interview with Joe Shoneman, Hermeus' principal flight dynamics engineer. I'm honestly surprised that Hermeus allowed us to upload this much of the interview. At one point, Joe gets a whiteboard out and starts explaining their flight optimization physics, and it took us up until now to get approval to share this information on YouTube. We upload uncut interviews like this to Nebula with every documentary we make. So, if you'd like to see more of them, subscribe to Nebula and check out the latest Nebula exclusive interview with Hermeus' CEO, AJ Piblica, which you can get access to for the discounted price of $250 a month. Or you can get lifetime access for just $300. This money helps us fund these documentaries, which takes us months to complete, and simply aren't profitable with YouTube alone. So, without further ado, get ready to listen to a fascinating conversation with Joe Shoneman.
My name is Joe Shoneman. I'm a flight dynamics engineer here at Hermeus. I joined the company last June, and I'm primarily responsible for handling qualities and flight performance of the Quarter series of aircraft.
What's your background in the industry?
So coming out of grad school, I had a focus on structural dynamics, and that's where I started. But really, a lot of my interests lie with how do you actually fly and employ aircraft, over the course of their mission. And at my past work, I was lucky enough to get into some work and research on higher speed systems. Got into some flight dynamics and wind tunnel testing of novel control systems for very high-speed missiles. And so that's what really got me onto the flight dynamics and performance path. And I started at Hermeus actually as a loads engineer, loads and flight dynamics. So really making sure that when we design the aircraft structure, we are considering the full range of forces that it might be subjected to. That in itself already has some tie into the flight dynamics aspect of our work, and recently have been able to pivot fully into flight dynamics, focus on making sure that the aircraft is going to behave the way that we want it to, and also that we can actually get the performance that we're looking for in hitting these touch point speed targets.
And what's been the biggest kind of change between working on missiles to like an actual aircraft? Obviously that's an aircraft too, but aircraft with wings.
Right, so oddly enough, I'll say there are certain similarities, especially when you compare them to rockets. So a big thing with rockets, rockets don't fly. Missiles, of course, use rocket motors, but at the end of the day, they're going to be gliding and flying and using aerodynamic maneuvering for the bulk of their trajectory. Now, the difference is aircraft are much more complicated. Missiles are generally symmetric. Depending on the missile, you will be in a number of different speed regimes, but the ones I was looking at were exclusively high speed. So with Quarter Horse, as with Dark Horse, we'll have to start off on the runway, take off under our own power, and go through that subsonic, through transonic, up to supersonic, and eventually your really high Mach 4, Mach 5 target Mach numbers. So just the asymmetries of the aircraft are significantly different. Certain effects that you might be able to get away with ignoring in a missile, you have to consider. And then the wide range of speeds is always going to be a challenge for this type of mission.
What is the main part of the aircraft that you're working on? It's like flight control, or is the structures?
I don't do the flight controls. I support that group. So I make sure that we're getting them the right data so that when they design the flight control systems, their controllers actually work across our flight envelope. So really, I'm looking at the aircraft at the system level, getting the aerodynamic data from our CFD analysts, where necessary, trying to baseline it against either known correlations or approximate methods, and really scrubbing through that, assembling the different databases that we need to provide to the guidance team. In the process of that, you don't want to just assemble them. You need to really scrub carefully through everything, actually look at all the different aero coefficients, make sure that you're understanding, make sure that everything can be explained. If it can't be explained, well, go back and check. Maybe you found something new, or more likely there's just a mistake somewhere that you need to rectify.
With CFD, obviously that can only go so far. Are you getting much real-world data as well to back that up? Like, how are you testing things?
So we've had one really great wind tunnel test that was performed, I believe, in January or February of this year. And that was a great baselining opportunity that really showed us that in terms of our static aerodynamic coefficients, the CFD models were doing a really good job of lining up with that test data. Now, a couple things there. First off, this was a static CFD test, or a static wind tunnel test. We distinguish static aerodynamic coefficients from dynamic aerodynamic coefficients, in that static works if you're at a fixed angle of attack, and maybe you go to another value. That's fine, that's static. But the rate at which you actually make that change also has a big impact in your aerodynamics. And that's actually one of the items, if we think back to missiles, you don't completely ignore those, but you can get away with many fewer dynamic coefficients than you can in the aircraft world.
Why is that? Is it just making less maneuvers?
I think it's some technicalities related to the speed that you're usually operating at relative to your length scale, things like that. Whereas aircraft, you have a much bigger length scale.
What's length scale?
Just the length of your vehicle with respect to your flow. For example, classic rate derivative would be your pitch rate damping, and that's related to the distance from your center of gravity to where your horizontal stabilizer is, if you have one. Because when you enter a pitch rate, your horizontal stabilizer is going to add some damping to your flight dynamics. That's typically a good thing. That's one of the many reasons you have a horizontal stabilizer, not far from the only one. But those rate terms tend to be related to the way that different surfaces are configured on the aircraft, and in some cases, even the rate at which you're changing your angle of attack or your side slip angle. So it's a really interesting, really complicated area, and because of the nature of them, those dynamic derivatives were not something we were able to get in the tunnel. Those are also a challenge to get in CFD, so that's often where, when you're looking at these types of things, sure, you can get them out of CFD using the state-of-the-art, but we often go back to just using the classical 1950s, 1960s, not quite hand calculations, but very, very close. So some classical methods. Talking about CFD versus tunnel testing versus your classical correlations and theoretical areas, static versus dynamic derivatives, that's a key one. Another thing I'll say is that wind tunnel test still isn't flight test. We can't always match Reynolds number. We can't always match the turbulent transition the way that we'd like to. And even you look, there's been some well-documented, I think my favorite well-documented miss in wind tunnel testing going to flight testing is actually from the SR-71. Some of the boat tail drag on the aft end of their engine injector nozzles, basically nobody accounted for it.
Well, what's boat tail drag?
So the transonic flight conditions, when the engine nozzle transitioned from cylindrical shape and then the nozzle necked down in its converging section, just that boat tail ejector region is where they had this issue. The airframe manufacturer thought that the engine manufacturer had accounted for it. The engine manufacturer thought the airframe manufacturer had accounted for it. Really, nobody had accounted for it. So they got into flight test and they had what they called a transonic surprise.
Okay.
It was an extra drag increment at transonic conditions that they weren't expecting. And I would be really surprised if at the end of the day, we get through our CFD, we get through our wind tunnels, we go to flight, and we don't see something like that. There's always going to be something new and interesting when you get to flight test. So that's the other item I keep in mind is, obviously we love testing, but ground test isn't flight test, and that's why getting flight hardware out the door into the air is really, really important.
Is there any major changes to the configuration that you see going from each of the iterations of the plane? I know Quarter Horse has a horizontal stabilizer. Would you see later generations just being like a...
That's certainly something, it's certainly a possibility. So I wouldn't go to say that I envision it, but it's something that's being actively traded. You can go look at past Mach 2 aircraft, and there's certainly plenty that have flown without a horizontal stabilizer. There's pluses there, there's minuses there. So
what you see as the pluses and minuses?
Well, so if we talk specifically, just to be concrete, let's compare the Mirage 3, which is a delta wing, no horizontal stabilizer, to maybe the F-104 or the F-16 came a bit later. The aircraft which did have horizontal stabilizers. There's actually a really great study that the French aerodynamicists published, the US translated it. So the benefit of the delta wing is mainly that you get less drag, simply because you're not having that extra lifting surface on there. The downside is because you don't have that horizontal stabilizer, you can't maneuver quite as well as you would or at least you can't pitch up to a maneuvering angle of attack quite as well as you would with the delta wing. But again, back on the side of the delta wing, you have a larger wing area because you're using more of that surface area of the vehicle for just for wing area. So there's a competing series that you go back and forth. You can pull to a higher angle of attack with the horizontal stabilizer, but then with the delta wing, you have more wing area at that angle of attack. In terms of maneuverability, what they found is that it largely cancels out those two competing advantages of pitching to a higher angle of attack versus the extra wing area. But they found it was a win in terms of just losing that drag. But that was something that they specifically needed simply because the engine that they had available was underpowered, whereas some of the engines of the other aircraft, they had sufficient power to be able to accept the drag hit for the delta wing, and they liked having the extra control authority. So it really is situation dependent. In our case, we have the engine that we have. It's the J85. And so that's what might drive us to trying to really get away from the horizontal stabilizer if we think we can afford it and go to a pure delta. But there's a lot of considerations there as well. There's robustness. It really comes down to robustness. Are we confident that we can rotate on takeoff under all circumstances that we might need to? Are we confident that we can hit the admittedly fairly minimal maneuvering requirements that we need to be able to go through for quarter horse? So it ties in not just with pure performance, but with the configuration overall. Where are you putting your fuel? Where's your fuel going with respect to your landing gear? How much fuel are you burning in flight? Quarter horse's only real mission is to accelerate up to that touch point. And so it is going to see a really substantial fuel burn in flight relative to its weight. So those are the key things that I would look at if we talk about, say, a horizontal stabilizer versus a pure delta wing.
What do you see is the biggest problem that you're trying to solve right now?
So the biggest problem we're trying to solve for quarter horse right now is how do we maintain, and I'll tie them together again, both our stability and our performance across the entire range of Mach numbers that we need to fly through. And this is probably one of my favorite parts of the problem, is this wide range of flight dynamic characteristics that we need to put up with for quarter horse. We're taking off under our own power. We start off in the subsonic flight regime, and that's certainly has complexity, but it's relatively well understood, fairly benign compared to some of the higher speed regions that we'll get into. The issues that we do have are that when we're going slow at takeoff and landing, we do have to get up into high angle of attack situations. You might have to contend with crosswinds. Some of the lateral aspects of your control system get to be really challenging there when you're at high angle of attack with a side slip. And we have to make sure that an aircraft, which isn't really intended for low speed flight, can actually be safely operated in that low speed regime. So that's our challenge at low speed. As we get up into the transonic regime, of course, transonic flow physics are always extremely difficult to contend with. Your control effectiveness tends to get more and more severe. Your center of pressure, or your aero center, I should say, begins to shift backwards. And so the stability of your aircraft is going to be affected up to low supersonic, where that aero center on the wing has shifted from its traditional subsonic position back to roughly the 50% chord marks. So by the time you get to supersonic, you've had a pretty large shift in the overall aerodynamic center of your aircraft. And depending on where your CG started, your center of gravity, that will present you with a couple different challenges. If you started with your CG forward at subsonic, you're going to be more and more stable, which you might think is a good thing, but the problem is you're going to have a trim drag penalty because it's going to take more control force to trim to a certain load factor. Even just trying to fly straight and level at a 1G load factor, you're still going to incur a decent trim drag penalty if you have an excessive distance between your center of gravity and your center of pressure, or your aero center. And I'll use them interchangeably, but they are somewhat distinct from each other. So aero center is more appropriate.
Yeah, I assume like you always want to have no trim drag as much as possible once you're at higher speeds.
Yeah, ideally you'd minimize it. And really any high-speed aircraft is going to pump fuel around for that CG management purpose. If you go back to the 50s and 60s, there's, I think my favorite oddball design, which never flew, was the XF-103. They had actual rotating, so not swinging wings, but rotating wings on a post for the purpose of trim drag management, which is
Wait, what?
fairly wild.
How did it rotate?
They had basically, if you imagine an all-moving stabulator,
Yeah.
it was an all-moving wing. So it could adjust the incidence of the entire wing with respect to the fuselage
I don't know how I haven't seen those before.
Or it never flew. I only found it looking at, old.
Yeah, and just like seeing the ones with like the forwards.
It's
wings and things.
Right. Yeah. It's a layer crazier than that because you're actually just rotating the entire wing.
That's cool. I did ask earlier of just like because of that issue with like the low speed performance and the high speed performance. Is a variable geometry wing something that has been, but I just imagine the complexity of the mechanics behind that are just a no-go?
I think the complexity in conjunction with all the thermal challenges that to be met really make that not something we'd like to pursue. And you can look, swing wings have largely had their day. Back in the 60s and 70s, your fourth generation mid-Cold War era, everyone wanted to go really, really fast. So you had all these swing wing designs and it's kind of boring. It ended up being that the weight penalty just wasn't quite worth it. So I don't want to say variable geometry of some sort will never be a factor, but certainly we're trying to minimize it for the quarter horse aircraft, at least, just out of simplicity. Of course, your inlet's always variable geometry, and that's just one of the effects you have at going to a wide range of Mach numbers is you need to deal with that.
The images I've seen of the quarter horse so far has the inlet like as that kind of like C-shaped at the nose of the aircraft.
Yep.
Quite unique looking. Is there any like reason it looks like that, like the shaping?
So I'll just say there's been a wide range of trade studies that have run, or that have been run. That, I believe, what you're referring to is what we call internally the ice cream scoop.
Okay.
Or the inward turning inlet is the more proper name for it. So that is one, historically you had your aerospike type cone inlets. Those could be handled with slide rule calculations as long as you had your conical shock theories down on paper. And then you had 2D ramp inlets, which could also be handled with oblique shock theory, which is even simpler. The inward turning inlet, I don't know the complete legacy of it, and I'm not the best person to discuss it. What I'll just say is that's a more modern concept that's really been enabled by CFD in order to perform. So you can't really study that inlet with any type of hand calculation. So there's other examples of that inlet out there in the literature, but it's really kind of a CFD-enabled type. That said, that doesn't mean that's what will end up going on the eventual Mark III. There's still trays that are being run, just like we talk about with the horizontal stabilizer.
Have you looked at the inlets with the variable cone and with?
Oh, absolutely. Yeah, there's been any number that we've gone through, full cone, half cone. There's pluses and minuses to each.
Is that, I imagine that's mainly a weight and complexity trade-off as well.
Weight, complexity, performance is one of them. So performance, you do get a performance impact, but for quarter horse in particular, we're in a spot where we're going to be favoring simplicity and just ease of execution over performance. So especially if you look at something like a 2D multi-ramp, you've got multi-ramps. So having multiple actuators with the loads that inlet has to sustain does get to be challenging. Doesn't mean it hasn't been done. F-15, F-14, those are multi-ramps. Not as large a Mach range, of course. XB-70, multi-ramp. But the simplicity of something like an aerospike is also really appealing.
With the issue of reusability in mind, what do you think the biggest challenge there is of like mitigating the issue of thermal heating?
So if we're talking about reusability specifically focused on aerothermal heating, I guess there's a lot of things I could go into on reusability. I would say for reusability, the biggest challenge is that we don't have the advantage of a rocket motor to boost us up to our operating point. And so again, we have to design for that wide Mach range. But thermal heating all on its own is, of course, an extremely significant challenge. But there's also going to be challenges in how we build things. And again, I'll call back to the SR-71 versus the XB-70, versus the X-15. So SR-71, you had a titanium airframe with a particular strategy to handle the thermal aero heating. They had, on the wings specifically, they had that beaded exterior surface, which was largely intended to mitigate thermal growth in the spanwise direction. They also had sliding joints in the chordwise direction. XB-70 took a completely different approach. They used stainless steel sandwich panels, so they really emphasized trying to keep a smooth OML with that much thicker section. And in the X-15, different class of aircraft, because it was rocket boosted, but they still had that essentially a heat sink Inconel skin. It was thick enough to absorb the heat up to the highest, high-end Mach numbers where they applied the ablative coating. But, with 3 different aircraft, 3 different airframes, 3 different material solutions, we're looking pretty hard at Inconel and titanium. The nice thing about Inconel is it's easier to take it up to the Mach 5 regime, whereas titanium, depending on your grade, really starts to struggle, even above Mach 4. So Inconel is a bit more future-proof, but it is heavier. It does have a higher coefficient of thermal expansion, so it introduces a lot more thermal stress into your airframe. And so that all has to be accounted for in your design process and your loads process. Quarter horse won't have to cruise at these Mach numbers, so that does mitigate the issue to some extent, but it does mean we're always going to be in a really transient situation where the temperatures are basically always changing. We're never really going to stabilize like you might get on a cruise vehicle. So trying to say, yes, we're going to compute every single thing aerothermally about this aircraft through its entire trajectory, that's where you'd like to be able to get to with a mix of ground test, flight test, and computation. But to try to be doing it before you've even flown, it's just really not feasible even with today's state of the art.
I assume there'll be a wet wing design for the larger versions, just for like a
very likely,
a range.
Just because of range and efficiency, yeah.
I saw, obviously renders aren't going to be completely representative of the final product, but with the kind of Air Force One render, it was white. I assume that's not how it's going to be.
So there are high emissivity white paints available.
Really?
If you can find the right emissivity, then in theory you could paint it white and get the same, say, 0.9, 0.95 emissivity that the black. It's not grill paint, but it's similar to grill paint.
Do you want to explain that problem? So I'm not
sure. So we'll just circle back. We're talking about the problem of what color do you paint a high-speed aircraft. And so just for background, and I literally watched your SSML video this morning. So
I know what the Kirchhoff's law of radiation and all that.
So, all right, the problem of what color do you paint your aircraft? For most aircraft, if it's a subsonic, you want to paint it something light, either a white color, potentially leave it unpainted, and that way it will not absorb too much of the sun's energy as you're hitting the ground, because the sun, the heat from the sun, is a key thermal source for most aircraft. As you get to higher Mach numbers, though, really anything above 2, the frictional heating, aerothermal heating from friction on the flat surfaces, and then your stagnation type heating on the front surfaces, that becomes a dominant source of the heating. And what you actually want to do to reject that is use radiation to your advantage. So instead of radiation from the sun coming in and hitting your skin and heating you up, you'll have radiation from your skin trying to leave. And the property that's important there, we call it emissivity, is you want to emit as much radiation from your skin as you can. And so emissivity is between 0 and 1. Perfect emissivity would be 1.0. And you can get a good emissivity of, say, 0.9, 0.95 with a nice black paint. And that's why the SR-71 you saw was painted black, classically the Blackbird. Now, what's interesting, and I don't know the total history of these paints, but there are high emissivity white paints available, such that you could buy a white paint and paint your aircraft white with that paint, send it to high speed, and still emit a good portion of that heat as radiation.
Would it be as high as the black? Would it be possible to get as high as 0.9, 0.95?
I've seen numbers of 0.9 quoted in.
Ever heard of that?
I'm not the chemistry expert. I just saw what was quoted in the guidebook. Other interesting thing is XB70, of course, was painted white. So did they just forego that benefit? I'm not sure. I'm not sure what their emissivity was. Yeah, regardless of the color of the paint, at the end of the day, what you want is high emissivity.
For something that's, again, long haul question, like the quarter horse is going to be doing that, but for a plane that's supposedly going to fly across the Atlantic or something, would you be able to fly at Mach 5 for a significant part of that with the heating, or would you have to throttle back if the heating started getting above acceptable levels for reusability and things?
The question of, are we designing for extended cruise Mach number, that is 100% the baseline. So we are targeting a long duration cruise for the majority of the flight envelope, or for the majority of a mission. The major exception to that will be the part of the mission where you're climbing and accelerating. That actually can take, depending on your weight, that can take a significant chunk of your downrange capability and of your flight time. But once we get up to cruise, yes, our thermal systems will be sized such that we can maintain that cruise, barring something going wrong, of course.
In terms of like fuel capacity and range, is it feasible to do like a single trip across the Atlantic without refueling midair?
When we get to a point where we do get into the detailed sizing for the New York to London type mission, yeah, that is something that I do think is going to be feasible.
Okay. What about, do you think like Transpacific would ever be possible?
Transpacific, to me, would be such a huge unlock in terms of connectivity. It's gonna be a bigger haul though. So I don't think aerial refueling for commercial flights is something to necessarily count on.
Right.
But you could be in a situation where you're able to cut that Transpacific flight into smaller legs,
okay,
which can be handled independently. I certainly don't at this stage want to promise a Transpacific route because the numbers start to get pretty imposing there.
One of the questions I really like to ask engineers, because I feel like it's one of the things that I loved about the job, is like it's ultimately a creative field. I think engineers are like ultimately creatives that are just mathematically inclined. And there's just those moments of like a dopamine rush when you create something new or you solve a problem, and it's like that kind of Eureka moment. Do you have any moments like that like stand out to you while working with Hermeus?
I don't know if it's necessarily a Eureka moment, but I think and in my opinion, is something interesting. I would say one of my favorite experiences of working on the Quarter Horse program was when we really started to get into trajectory optimization, and this was in conjunction with the guidance team. So there's a metric called fuel-specific energy. It's related, or fuel-specific excess power. And basically it tells you if you're trying to climb and accelerate, how many feet of energy altitude can you add for every pound of fuel burn. And it's a classical aircraft optimization metric. There's nothing new there really. But the first time we were able to apply it to Quarter Horse and combine our models, our aerodynamics models, with our propulsion model and our mass and weight breakdown for the aircraft, and generate a diagram of fuel-specific energy across our entire envelope, it was just one of the most beautiful plots that I've ever seen. And what's great about it is that not only does it look really interesting, it actually tells you where you want to fly the aircraft to most efficiently make it up to your target Mach number and altitude. And so without that available, you're to some extent operating in the dark. You can do different types of optimizations. You can use your judgment. But that particular step forward in our trajectory optimization was one of my favorite moments. And even better, it actually unlocked a world of not just trajectory optimization, but a better world of understanding of how do we take Quarter Horse in a better direction to be able to better achieve this mission. So there was a good deal of understanding that went through there, and that's one that I would point to as one of my favorite moments, was just that bringing in that, again, classical 1950s, 1960s era climb optimization into the 2020s with all the benefit of the manufacturing and the computational capabilities that we have today.
What is that plot? Is it like an altitude speed thing, or?
Yeah, is a whiteboard session like, okay? I don't know
if you're allowed to, we can turn it around.
All right, so we can talk here about climb optimization for the Quarter Horse aircraft, and there's a few metrics we care about. First one you might care about is excess thrust. Oh, all right. And that's just your thrust minus your drag. So that tells you how many pounds of extra thrust you have available at a given point in time. It's useful, but it's not the whole story. Next up, you have specific excess power. So this takes your excess thrust, multiplies it times your airspeed, and then divides it by your weight. This will be units of meters per second, since I know you prefer metric, whereas excess thrust, of course, you started in newtons. So this tells you how much excess power you have either to climb or to accelerate. Interesting fact, if you use all of your excess power to climb, the excess power is simply your climb rate. If you're using it to accelerate, things get much more complicated, but it's your next nice metric. If all you care about is time to climb, all you want to do is maximize specific excess power during the ascent. But the most interesting one to me is fuel-specific energy. And so this is going to take your specific excess power and then divide it by the amount of fuel or other consumables that you're using per second. So this will end up being meters per, not per pound, per kilogram if we're doing weight. In other words, if you want to know, this will tell you how many kilograms of fuel it takes to gain 1 meter of energy altitude.
Right.
Last thing we need to know is energy altitude. This is just your actual altitude plus the kinetic energy contribution you have from your given airspeed. So all that said, what you can do with this is draw a big contour. I'll put Mach on the x-axis. It might be slightly more appropriate to use raw airspeed, but Mach is nicer to think about. And then we can have altitude on the z-axis. I won't use any numbers here. We'll just say, hey, if this is 1, the rest can be whatever. Typically what you're gonna have is, well, first off, you'll have energy altitude contours that look kind of like this.
Okay, yeah.
So clearly, if you're at some high altitude with no airspeed, that's equivalent to some higher airspeed with no altitude. And then I'll just use blue and red to represent the fuel-specific energy contours that you might want to plot. So typically, you're going to have these contours will be closed circles on this diagram. So you'll have areas of good performance. And as you get to Mach 1, you start to really have areas of bad performance. And in fact, there'll be certain regions where you can't fly, either because your dynamic pressure is too high, or you're simply stalling out.
Like flight windows, essentially.
Or your propulsion system just doesn't work well. And so you have this kind of bad zone you want to get through. And if it was a regular engine, that would be the end of the story, right? You can't just keep accelerating, your engine can't do it. But because of our technology, our pre-cooler and eventually our ramjet, we actually start to get performance back at some higher up Mach number. So we, start to expand out this region. And again, we'll have areas where things are kind of the best, and then performance starts to taper off. Eventually, of course, at a high enough Mach number, we just can't really go any further. So imagine a much more colorful, more physically accurate version of this, and that's what these contours look like. What you end up wanting to do is, if I can avoid butchering the explanation, you basically want to fly where these contours are good, right? You want to fly in areas of high fuel-specific energy, because that means you're getting lots of energy altitude per kilogram of fuel that you're burning. So we want to fly through these good areas. And really interesting technique that's been applied in the past. So I believe SR-71 did this twice, actually, during its ascent. When you get into these bad regions, you want to dive along contours of constant energy altitude, which I think makes intuitive sense, right? But running through the math and then seeing it represented mathematically can be just really satisfying, really interesting. And that's going to let you minimize your fuel burn as you continue up to wherever your target point happens to be. So when we talk about the fuel burn that we use during climb, this really is the quarter horse mission, right? We get to here and we're done. We get back to base. If you are a dark horse, then you want to get here and cruise afterwards. But for quarter horse, this really is the story, is how do we design our aircraft to be as efficient as possible across this Mach altitude range, not at any one given Mach number, but at the entire range of Mach numbers, so that we can go through this envelope, climb as efficiently as possible, and get to this touch point.
So for this, the actual physical, like the representation of this in real life would be, you're essentially trading potential energy for kinetic energy during that bad region. Am I understanding that right?
During the bad region, right. You want to you want to use that trade-off to your advantage to basically shortcut off some of this bad region. And the exact proportion, you might get through more of it, but any any older engine like the J85, it is an older engine, right? So most aircraft with an older type engine will have to do something like this. Now, if you have an F100, things look completely different, and you can just really blast right through that region. So Dark Horse is a different story, but Quarter Horse, in terms of the engine we have available, the level of simplicity we're trying to retain, which I referenced earlier, we do end up with this really interesting climb optimization problem that's been a pleasure to work on.